All right, so just to pick up from last time, let's do a little example to kind of make sure we have internal energy, heat, and work, down packed. So let's say there's a balloon that's being inflated. So balloon being inflated. And it's being inflated to its full extent by heating the air inside it. By heating air inside. Okay? So inside. All right? In the final stages of this process, the volume of the balloon changes. So volume is going to change from, so we're going to call that V1, 4.00 times 10 to the 6th liters, to, so volume 2, to 4.50 times 10 to the 6th liters, by an addition of, so we're adding 1.3 times 10 to the 8th joules of energy as heat. Okay, so if we assume that the ball is going to expand against a constant pressure, right, at 1 atm, because that's very key, this has to be constant pressure. All right, so if it's at constant pressure, meaning 1 atmosphere, then what is the delta E, or the change in internal energy of the process? So what is delta E? Right? So what are we going to do? The first thing is, well, we need to know the conversion between joules and liter atoms. Just another way of calculating the energy. Okay, so we'll get to that in a second. But first thing we need to know is, what do we know so far? And we wrote all of our givens right here. We know all of this. So another way we can say this change in energy as heat is Q. So Q is equal to positive 1.3 times 10 to the 8th. Pressure, we said, was 1 atmosphere. Okay. The other thing we need to know is that 1 liter times atmosphere is equal to 101.3 joules. That's just a conversion that they should probably give you anyway. Okay. So again, our equation is delta E equals Q plus W equals Q plus W. All right. So what is the work that's done on the gas? That's the first thing we need to know. So the work that's done on the gas is going to be negative P delta V. So what's delta V then? Delta V was the change, so V2 minus V1. And in this case, that's going to be 4.5 times 10 to the 6 liters minus 4.0 times 10 to the 6th liters. So that leaves us with 5 times 10 to the 5th liters, and that's delta V. Right? So then the work then, if we just plug that in, and we know that pressure is going to be 1 atmosphere, right? So W is equal to negative times 1 atmosphere times 5 times 10 to the 5th liters. So work is just basically 5 times 10, negative 5 times 10 to the 5th liters times atmospheres. Now notice this is in liters times atmospheres, right? So be very wary of the units, because sometimes the units will actually help you solve the problem. All right, so the negative sign in this case makes sense because we know that the gas is expanding. We said that when the gas is expanding, then it's doing work on the surroundings, meaning the system is doing work on the surroundings. So to calculate delta E then, we need to sum Q and W. So Q is going to be given in joules right now, so we need to convert that, right? Or we can just convert this work into joules. So let's do that. Okay, so then work is going to be basically negative 5.1 times 10 to the 7th. Then basically doing delta E is very simple then. Delta E, Q plus W. Remember, Q was positive 1.3 times 10 to the 8th joules plus negative 5.1 times 10 to the 7th joules. So delta E is equal to delta E is equal to 8 times 10 to the 7th joules. Okay, so that is the change in internal energy. Okay, so does this make sense? Since more energy is added through heating than the gas expands doing work, then there's a net increase in internal energy of the gas in the balloon, right? So that's why delta E is going to be positive in this case. All right, in the next video, we're going to basically talk about enthalpy and calorimetry.